let me talk about the test. And then there's one more little topic that I want to go into on 2D kinematics, and then we're done with that. If you have any questions about problems on 2D kinematics, I'd be happy to answer some. And when you're done with questions, we're going to go on to the next topic, which isn't going to be on the exam. So, exam 2 is on Tuesday, the 10th. 10/10, my 13th wedding anniversary. Thanks. Thank you. Yes. 13. Lucky 13. I hope we make it. Thank you. Thank you. The topics are everything up through 2D kinematics. Yeah, everything. It's all cumulative. So remember to look back at old stuff too. But you don't have to worry about any of the stuff from labs. That's totally separate. Okay. But everything up through 2D kinematics. And so today we're going to finish 2D kinematics, and when we're done with that, the next topic is 2D kinetics. So we're finally going to get into the causes of the motions, talking about mass and force and how those relate. So if you noticed on D2L, I said that you should work on all the 2D kinematics problems except the first one. I didn't list the first one yet. So what I'm going to talk about today is something we're going to do. Most of the time we're going to spend on it is going to be in labs, but it will sort of help you with that first problem. So let me go through that. So this is an intuitive understanding of acceleration in 2D. And I know everybody is, becoming familiar with the fact that acceleration is a hard thing to imagine. Velocity is much easier to imagine. The direction of velocity is the direction something's moving. The magnitude of velocity is the thing's speed. That's pretty easy to wrap your head around, but acceleration is a lot trickier. In 1D, you can sort of wrap your head around it as long as you think of it in terms of the thing speeding up or slowing down, how that relates to the signs of the velocity and the acceleration. But in 2D, you can't even, that's not even enough. So I want to talk about how to think of acceleration in 2D. So first of all, this is in 1D or 2D or 3D. We're not going to do 3D problems, but 1D or 2D. If the velocity is constant, acceleration is 0. You can think of those two statements as meaning the exact same thing. 0 acceleration is constant velocity. So if something's moving in a straight line and its speed isn't changing, there's no acceleration. And if you think about when I first gave that original definition of acceleration, acceleration measures how quickly velocity is changing. So if velocity isn't changing, acceleration is 0. But if you have non-zero acceleration, so if the velocity is changing and you have acceleration, in 1D, that could only mean that the thing is either speeding up or slowing down. That's all there was in 1D for acceleration. But in 2D, there's something new that acceleration can do. So first, it can still do this. And this new thing is it can also cause objects to turn. So if the direction of the velocity is changing, that's also acceleration. In 1D, there was no such thing as turning because you're stuck on a path. But in 2D, you have a lot of options where to go, and so turning is a thing. And now that acceleration means two things, it makes it a lot, you need to be a lot more disciplined in how you try to imagine what acceleration is. So let me give you a set of steps for sort of visualizing the direction of acceleration. Steps for visualizing the acceleration direction. So the first thing you have to do is draw the object's path. So if the object's moving in a circle, you draw a circular path. If the object's going over things like this, you draw a path that just tracks the motion of the object. Then at the instant that you're interested in, because acceleration is an instantaneous thing, instant of interest. You can draw the direction of the velocity vector. It's always tangent to the path. So draw the velocity vector tangent to the path in the direction of motion. Third, if the object is speeding up, draw the parallel part of the acceleration. So I'm going to call it A parallel. And if it's speeding up, what do you think, based on what you know from 1D, do you think A parallel is in the same direction as the velocity or the opposite direction of the velocity? Same, yep. So draw A parallel in the same direction as the velocity. And if the object is slowing down, draw it in the opposite direction. Okay, so that's step 3. That's where we figure out the part of the acceleration that makes it speed up or slow down. Now in part 4, we're going to figure out the part of the acceleration that makes things turn. So now we're going to draw, I'll call it A perpendicular, and draw it perpendicular to the velocity vector in the direction the object is turning. And then now that you have the parallel part of the acceleration, the part that's parallel to the velocity, and the part that's perpendicular to the velocity, the total acceleration is just the sum of those two. So the total acceleration is just A parallel plus A perpendicular. I'll do a few examples. Anybody have any questions yet about that? But notice that step 3, that part where you figure out the direction of the parallel part of the acceleration, that's something that you can do in 1D also. It's just step 4 that doesn't exist in 1D. Okay, so first let's imagine a ball rolling up a ramp, and it's under the influence of gravity. So we want to try to figure out what the total acceleration vector looks like. Okay, so first I'm going to draw the path. So the path this object's following looks like that. If it's rolling up the hill, what direction is the velocity vector? Up the hill. It's going to be parallel to that path. So I'll draw the velocity vector like this. And now we have to draw the part of the acceleration that's parallel to that velocity vector. Would this be speeding up or slowing down? Slowing down. So do I put A parallel in the same or opposite direction of the velocity? Opposite. So there's A parallel. And now, is this object turning? No, it's following that straight path, right? And so there's no A perpendicular in this case. So A perpendicular is 0. So now the total acceleration vector is just equal to this vector plus 0. And so you just get this vector. And so in this case, that's the direction of the total acceleration vector. That's actually something we've done in 1D before, right? This, and really what this is a 1D problem. And so that's why the turning doesn't come into it. Okay, so now let's do one where it does turn. So let's say now we have a ball that's rolling down a circular path. path that this ball travels is going to look like this, right? The velocity is going to be tangent to that. And so a tangent line to that path where the ball is right now looks like that. Would it be going this way or that way? Up or down? Down. So I'll draw this tangent velocity vector tangent to the path. So that's the velocity vector. Would this ball be speeding up or slowing down? Speeding up. So is the parallel part of the acceleration in the same or opposite direction of the velocity? Same, so I'll put that here. It's parallel to the velocity. So that's a parallel. And now this one isn't moving in a straight line. So we have to think about which way it's turning. It's either to stay on this path, this straight path, it's either turning, it has to be, this perpendicular part has to be perpendicular to these two. So the only question is it turning this way or this way? You have a feel for that? Yeah, it's turning towards the center of that circle. If you can visualize like a center of curvature of this thing, like the curve that something's on being part of a big circle, it's always going towards the center of that circle. You could also picture, like if you imagine this being a top-down view of someone driving, you can imagine that driver would be turning to the left to stay on that path. Okay? And so it has to be to the driver's left. But so the perpendicular part looks like this. And now the total acceleration is equal to this plus this and so the acceleration vector is in this direction. Okay. There's one issue with this, though. That would be the direction of the acceleration if we knew the magnitudes of these two. But we don't. All we know is, we don't know how much it's speeding up compared to how much it's turning. You can do calculations to figure that out, but that's not part of this intuitive way of thinking about it. So what can we say about the direction of the acceleration if we don't know the magnitudes of these two? Yeah, remember, so this is, when we did these exercises in lab, this is why we were doing that. We know that we're adding up a vector in this direction and a vector in this direction. We don't know what the magnitudes of those two are. So all we can say is there's a range of possible directions of the total acceleration. And that range looks like actually it's a range of possible directions for A. And it looks like this. This one's in the direction of the parallel part, the green vector. This one's in the direction of the blue vector, the perpendicular part. And it could be anywhere between those two. So based on this analysis of that motion, we can say that the acceleration is somewhere in this 90 degrees. It definitely isn't outside of that 90 degrees. Anybody have any questions yet about this? We'll do a couple more examples. But remember doing that in lab? And here it is in class. Totally different thing. But you do it the same. Yeah, exactly. Thank you. Thank you for that. Okay, so now let's do another one like that. So now let's say okay, so let's say, what did we just do that it's going down? So let's do this one going up the ramp. So the path that the ball is traveling would look like this. The velocity vector is tangent to that path. So like that. Would it be speeding up or slowing down? If it's, well, it's going up the ramp. So yeah, so it's slowing down. And so there's the parallel part of the acceleration. Would it be turning this way or this way? Yep, toward the center of that circle. So there's the perpendicular part. And so if you add up a vector going in the green direction and a vector going in the blue direction, it can be that way or anything in between. So those are the possible directions the acceleration can be. Any questions about that? Why wasn't there, in this first example where it was just going up that ramp, why wasn't there any uncertainty in the direction of the acceleration in that one? Yeah, that's right, because it wasn't turning, there was no A perpendicular, and that means that we weren't adding two unknown things. We just have one unknown thing, and no matter how long this is, it's still going in that direction. Okay? So in this case, we knew exactly what direction the acceleration is. We don't know the magnitude unless we do a calculation. It's only the ones where it's speeding up or slowing down and turning that you have that range of possible directions. So let's do one more example. So for this one, let's say it's like a bird's eye view of tetherball. So here's the pole, and here's the ball, and the ball's following a circular path like that, except a circle. Can you picture what I'm drawing? Okay, and let's say it's going around the path this way. And let's say that this is moving with a constant speed. Okay, so while this circle, this big circle I drew around the outside is the path that the ball's following, so that's already there. The direction of the velocity is tangent to this circle, so something like that. Moving with a constant speed, so it's not speeding up or slowing down. So there's no parallel part of the acceleration. So A parallel is equal to 0. What direction is it turning? So this vector has to be perpendicular to B, so either this way or that way. Toward the center of the circle. So the parallel part of the acceleration, the perpendicular part, A perpendicular, is that. And so the total acceleration is equal to this plus 0. And so it's this. And is there any uncertainty in the direction in this case? There's not, because again, the uncertainty only comes up when you're adding two vectors where you don't know the length. This one, we don't know the length of this, but we know the direction is that. And so what this says, this is something that's going to be important later on, is notice anytime an object moves in a circle, constant speed, the acceleration is towards the center of the circle. So we'll have a whole section where we're doing calculations involving circular motion, and this is going to be sort of a key idea. Any questions about that? Okay, so that's the end of the stuff that's relevant for the test. Does anyone have any homework questions or anything? I'd be happy to answer some questions. Yeah. Yeah, do you have it with you? Oh, the helicopter. Okay, so this helicopter is moving 20 meters per second at an angle of 15 degrees above horizontal. And okay, this velocity is 20 meters per second. An object's dropped when the helicopter is 55 meters up. And it asks a few things that are pretty similar to what we've been calculating. Maybe I'll skip those. But the last one is different from other stuff that we've calculated. So it says, what's the velocity? What's the object's velocity vector when it's released? How long does it take to hit the ground? How far will it travel horizontally before it hits the ground? And unless anyone has any specific questions about these, I'm going to skip these three. The one that's different than what we've seen is how much higher will the helicopter be when the object lands? Okay, so we're asking basically, like, we know when the helicopter drops the object's 55 meters high, okay? Maybe when the object lands, the helicopter just keeps going along its straight path, okay? So when the object lands, let's say the helicopter is at a height of 75 meters. I think it's something like that, okay? So what we want to know is the difference in height from when the thing is dropped to where the helicopter is when the thing hits the ground. And if the helicopter is 75 meters high when the thing hits the ground, the answer would be 75 minus 55, 20. Okay. But so how do we calculate that? Well, the first thing we have to know is how long it takes for the object to hit the ground. And we did that in part B. Is that 3.91 seconds? Yes. I just did that in my head. Not really. I've done these problems a few million times. Okay. And so now we're not talking about the motion of the object that's dropped anymore. We're talking about the motion of the helicopter. And the helicopter is not in free fall, hopefully. That's like one of the last things you want to do as a helicopter pilot. That's like all of helicopter school is designed to keep you from being in free fall in your helicopter. So the helicopter is not in free fall. It has constant velocity. Okay, so, and its velocity we can figure out from what it tells us at the beginning. We know so the velocity is 20 meters per second times the cosine and sine of 15 degrees. Do you have those in front of you, those values? 5.176? Okay, so the helicopter keeps that velocity vector the whole time. And So now we're going to figure out how high the helicopter is after 3.91 seconds. So we're going to choose time equals 0, time final, origin location, axis orientation. So time equals 0 is when it's dropped. Time final, this doesn't happen very often. I guess there are some other problems where you have this. But in this case, time final right at the start, we know it. Time final is 3.91 seconds. And that's what we're trying to figure out is after 3.91 seconds, how high is the helicopter? The origin, I said I always put it on the ground below where the thing is at time equals 0. I don't think that's how I did it in my solutions, but let's do it that way here, okay? So let's say it's on the ground, beneath the object, at time equals 0. And then the coordinate system will do the usual thing with y up. Now we have to think about what we know and what we want. We know time final. Do we know anything about the initial position? Yeah, we do. We know both of these. We know that since we put the origin right underneath the helicopter, we know that PIX is 0. And we also know it's 55 meters up, so PIY is positive 55. Yeah, that's just because I chose a different origin location. So you can do it either one of those two ways. Yeah, I chose them that way for the first part too, I think. Or no, I didn't. Oh, well, that's a mistake then. But you can do it with origin on the ground, or you can do it with the origin where the helicopter is when the thing is dropped. So I'm going to do it this way just to be consistent with the way I've been doing all the other example problems. Do we know anything about P final? Remember now, we're not talking about the object, we're talking about the helicopter. So we don't. And what we're trying to find is PFI. Do we know anything about the initial velocity? Yep. We know that the velocity is constant, so VIX is equal to 19.319, 5.176. Whoops. So the X component is the 19.319. The Y component is the 5.176. I have it written here like that. Okay. What about the final velocity? We do know those because it's constant velocity. I'm going to leave them off because you can think of constant velocity and zero acceleration mean the exact same thing. And I'm going to instead write that we know the acceleration is 0, so that's kind of redundant to have them both. So AX is equal to 0 and AY is 0. So why is AY 0 in this one? Yeah, because the velocity is constant because this isn't a free fall problem. We're tracking this motion of the helicopter. So is there an equation that works with these? I think this one should work. PFY is equal to PIY plus VIY TF plus 1/2 AY TF squared. So PFY is equal to 55 plus 5.176 times 3.91 plus AY is 0, so that term is 0. And what do you get for this? 75 point something, I think. 75.28 meters is the final position. That's not exactly the answer that it asks for. The problem asks how much higher is it at the end. So what we want is the y component of the displacement, really. We want 75.28 minus the starting height, so 20.28 meters. So that's how much higher the helicopter got in the time that that object was falling. Any questions? Yeah. Yeah. You want to? Let's do it the other way and put the origin in a new. We'll put the origin where the helicopter is when the thing's dropped, and we'll just see how it compares. Okay? Because you can do this problem either way. Okay? So I could have also put the origin at the object's location when time is equal to 0. So everything else will keep the same, but this will change. So now let's think about what we know and what we want. Time final is still 3.91. P initial, now both components are 0. P final y is still what we're trying to calculate. V initial is still 19.319. And VIY is 5.176. And the acceleration is still 0, 0. And so now we use this equation. PFY is equal to PIY plus VIY TF plus 1/2 AY TF squared. So we get 0 plus 5.176 times 3.19. And that answer is 20.28. So based on that origin, the height at the end of the motion is 20.28. But now, we're trying to figure out how much higher it goes, which is the y component of the displacement is the final position, y component of the position, minus the initial y component, which is 0. So we get 20.28, which is exactly the same as it was with the other origin. So any question that's asking for a displacement or a part of a displacement, if you put the origin where the object starts, then your final position is the displacement. But it's not really, either way, you just have to subtract at the end. So it's not worth like going out of your way to change the origin just so you can skip one subtraction, you know. Any other questions about that problem? Any other problems you'd like to see? All right, well, let's do half an hour of new stuff. So none of the rest of this stuff is going to be on the test, but it's the most important sort of single topic in this class, so you still should listen. So the new topic is kinetics of particles in 2D. So the distinction we're making is between kinematics and kinetics. Who remembers what kinematics means? That's right. Exactly. So kinematics is a description of the motion that doesn't deal with the causes. And so kinematics is just relationships between time, position, velocity, acceleration. It's all stuff that from a carefully done video, you could take all these measurements. Like if a video camera watching something move, you could take all these measurements. Kinetics is, so kinematics is still part of kinetics, but now we're going to add causes of the motion. That's stuff you can't figure out from just watching a videotape. And those things that, the new things that we're going to introduce with kinetics are mass, force, and a little later on we'll talk about energy. So before we start going into calculations involving kinetics, I have to introduce these new terms. So first I'll do mass. That's the easier one of the two to wrap your head around. So, you know, how do you think, you don't have to say it out loud, but how do you think you would describe mass? Like, how do you think mass is measured? Well, in a way, like the fact that bathroom scales have a setting on them that, so like the one in our bathroom, you can switch it from pounds, which is a measure of force, to kilograms, which is a measure of mass. And so you get this sense that like the force applied by gravity and your mass are the same thing. They're different things though. And so what mass really measures is an object's resistance to acceleration. If you take any two objects and isolate them from other forces, so you know you could put them on rolling things that don't weigh very much and don't have much friction, and bounce them against each other, the object that has more mass is going to accelerate less. The object that has less mass is going to accelerate more. The more massive object is more resistant to being accelerated. And you know, so this is like a semi and like coming towards a little car. So you know that this collision is going to go fine for the semi and go really badly for the car. The reason that that's going to happen is, you know, what I was just describing. The truck has a lot of mass, and it's very hard to make something with a lot of mass accelerate. The car, compared to the truck, has very little mass, and it's really easy to make it accelerate. And so when those two collide, the truck is going to, what it means if you don't accelerate very much is the truck is going to stay pretty close to its original velocity. You know, it's going to slow down a little, but it's going to keep going this way. The car is going to go from having a velocity in this direction all the way to having a velocity in this direction in the same amount of time, and that's a huge amount of acceleration. Okay. You know, bathroom scales, a bathroom scale to work depends on gravity. So, and getting accurate weight measurements for astronauts is actually, turns out it's super important because you can lose bone density if you're not careful, being, you know, not having to deal with gravity day after day. And so astronauts every day are like weighing themselves to try to make sure this isn't happening. And but how do you measure your mass in a place where there's no gravity? You can't do it with like a bathroom scale or a balance or anything like that if there's no gravity. And the way that you do it in space, I've never seen the thing, I've only heard it described, but you get in this big contraption that applies forces to you. Like I picture it being like one of those things that like women in the 50s used to be on while they watched soap operas. Like, I don't know if it's like that, but that's how I picture it. And it shakes them back and forth. And based on how hard or easy it was to accelerate them, it can measure their mass. So what mass really is the ability to resist acceleration. Okay. Notice that mass is always a positive number. And so that means that it's not a directional quantity. There's no such thing as an object that has a mass of 100 kilograms in this direction and a mass of 50 kilograms in this direction. It's just a single number that describes its resistance to acceleration. And the SI units for mass are kilograms. You might think it's a little weird that the SI unit has the prefix kilo on it, like it might make more sense for it to be grams, but that's how it is. And then the little bit more complicated new quantity that we have that you can think of as like a cause of motion is force. Um, and force is a vector, so it does have direction. That measures the intensity and direction of push or pull on an object. So if something's pushing or pulling harder on you, stop pushing me. They're applying a force. And if they're pushing you harder, they're applying a bigger force. Okay. The units of force are units of mass times length over time squared. And so SI units for force would be kilogram meters per second squared. And force is a quantity that we use all the time, and that's a really cumbersome unit, so it was given its own name. So 1 kilogram meters per second squared is equal to 1 Newton. But a Newton is 1 kilogram meter per second squared, and it's abbreviated N. In this class, there are only two, so I'm going to separate forces. Like, pretty soon we'll go into all these different types of forces. Forces from the ground pushing up on things, and friction forces, and weight forces, and all these different things. But for now, I want to split up all the forces that can act on an object into just two categories. The first one is the weight. That's the force applied by gravity. And once you've dealt with the weight, the force that gravity applies to an object, the only other things that apply forces to objects are things that are making physical contact with its boundaries. So things, I'll just call it contact with another object. So for us, what are the forces? How many forces are acting on that table right there? Gravity is always acting on things, so there's a weight force, that's one. And then just look around the boundary of that table and see if anything's touching it. The chair is not touching it, by the way. So the only thing touching it is the ground. So there are only two forces acting, the weight and a force applied by the ground, and that's it. Okay. There are some other forces that can apply that we're just not going to deal with in this class. Magnetic fields can apply forces, electric fields can apply forces. We're not going to talk about that, but it doesn't really change anything very much. Okay, so going back to the bathroom scale thing. So I introduced these two new quantities. One is mass and one is force. They're totally different things. Uh, they don't even have the same units. So how is it that your bathroom scale can switch between calculating pounds, which is a measure of force, and kilograms, which is a measure of mass? Um, well, uh, we're going to see that the weight, the force that gravity applies to an object, is dependent on the mass. And so as long as you know what gravity's relationship is to mass, you can figure out what the mass must be based on the force that's applied. And so the number crunching inside the digital scale or whatever, or just the way the dial is set on the spring scales, it's all based on the assumption that you're roughly at sea level on Earth, and so gravity's relationship to mass is this fixed relationship. But if you took a bathroom scale to the moon, it would give you an accurate reading of the force that you're applying to the scale. That would be totally right, and it would say 18 pounds or something, but it would give you a totally inaccurate measure of what your mass is. Your mass is the same on the moon as it is on Earth. You just apply a lower force to a scale because gravity isn't pulling as hard on you. So it's a weight loss tip that you'll only hear here in physics class. Go to somewhere with weaker gravity. It works. I do it all the time. It doesn't help your pants fit, though. Okay. So let me introduce Newton's second law. So when we started talking about vectors, we did talk a little bit about the orientation of coordinate systems and how you can use different coordinate systems. But all we cared about when we were talking about vectors was we only cared that the coordinate system had perpendicular axes and that it was rotated, not flipped. But now for kinetics, there's a new requirement for coordinate systems. So for doing the calculations in kinetics, there's a new requirement for systems. They must be what's called inertial. Be inertial. And what that means, an inertial coordinate system has two requirements. The origin isn't accelerating, and the axes aren't rotating. Okay, so you can always think of a coordinate system as like a video camera that's taking measurements. And what this says is to use our kinetics calculations, you could use measurements that you get from a video camera that's fixed to like the wall of a building, and all of the kinetics equations would work. But if you have your coordinate, okay, but now imagine that you have a video camera inside a truck, okay? Inside like a semi truck that with an open back, like a Knight Rider, where you have room in the back, or like an RV. You know what I mean? So the video camera is fixed inside there, and say you can't see that the truck's moving through the video camera. Everything's, you can't see the road going by or whatever. But if this video camera is taking measurements of what objects are doing inside that truck while the truck is accelerating or turning, the measurements that that video camera took would not satisfy the kinetics equations that we're going to use. It would look like the laws of physics were being violated. Okay, so that's what it means to be an inertial coordinate system. The video camera taking the measurements can't be accelerating or turning. Okay, and if the coordinate system is inertial, you can think of the force vector defined this way. So this is called Newton's second law. I'm going to abbreviate it. I'm going to talk about it all the time, so I'll abbreviate it N2L just for make it a little quicker. And what Newton's second law says is if you add up all the forces acting on an object, that's the net force, that's equal to the mass of the object times the acceleration vector of the object. And let me define all these values here. So F net is the sum of all the force vectors acting on the chosen object M is the mass of the chosen object. And A is the acceleration vector of the chosen object. So Newton's second law is the most important equation in this class. We'll use it for the rest of the semester. And I would say probably there are probably three candidates for that people would say are the most important equation in all of physics, and this is one of them. You know, so this is hugely useful. And notice that in all of these expressions, I keep talking about the chosen object. It's going to be sort of a key thing in using second law, Newton's second law, that we're very clear to ourselves about what our chosen object is and where the boundaries of that chosen object are. And a lot of the approaches that we're going to use to using Newton's second law are based in trying to be just really clear about what the boundary is of our isolated object. Anybody have any questions about Newton's second law right now? Okay, well, so this is what we're going to work with. That's it for today.